Let's try problem 12.36. Alligators and other reptiles don't use enough metabolic energy to keep their body temperatures constant. They cool off at night and must warm up in the sun in the morning. Suppose a 300-kilogram alligator with an early morning body temperature of 25 degrees Celsius is absorbing radiation from the sun at a rate of 1,200 watts. How long will the alligator need to warm up to a more favorable 30 degrees C? Assume that the specific heat of reptilian body is the same as that of a mammalian body. Okay. So there's one lookup you need to do, is the specific heat of the reptilian body. We're told it's the same as the mammalian body. And so if we go over to table 12.4, you can see that the specific heat is actually, so C is equal to 3,400 joules per kilogram Kelvin. Okay, so there's also a couple other things we need to realize. So the mass of the alligator, so the mass is going to be equal to 300 kilograms. And the body temperature is going from 25 C to 30 C, which is a change in temperature of 5 degrees Celsius. But since we're given this constant down here in Kelvin, 5 degrees Celsius is just the same thing as 5 degrees Kelvin. And the last thing, we know that we're absorbing radiation at a rate of 1,200 watts. So that's going to be our power. It's going to be equal to 1,200 watts. Okay, so our next step is just going to be to figure out the time that he's going to need to be in the sun for. So if you remember, we have an equation for power, which is equal to the change in energy over the change in time. But for this problem, our change in energy is just going to be heat, the heat from the sun, or the radiation from the sun, right? So we can rewrite this as power is equal to Q over T, delta T. And if you'll notice, we know delta T. Oh, we don't know delta T. We're going to try to solve that for that, but we know P, and we can get Q. So let's just rearrange this first. So multiply delta T to both sides, and divide both sides by P. We get delta T is equal to Q over P. And in this chapter, we learned that the heat can be written as equal to the mass times the specific heat times the change in temperature. And this is still going to be over P. And so we know all these things now, right? We know the mass of the alligator, 300 kilograms. We know the specific heat of the alligator, which is 3,400 joules per kilogram Kelvin. And we know the change in temperature, which is 5K. And we know the power from the sun, which is 1,200 watts. And so all I have to do is just fill in now. And so this is equal to 300 kilograms times C, which is 3,400 joules per kilogram Kelvin, times delta T, which is 5 Kelvin, all over power, which is going to be 1,200 watts, or joules per second. And so if you notice, a lot of our units cancel here. Kilogram is going to cancel with kilogram, Kelvin is going to cancel with Kelvin, and then we have joules over seconds, so the joules are going to cancel out, and we're just left with 1 over seconds, which is going to be seconds, so we're in the right units. And so when you plug this in your calculator, this comes out to 4,250 seconds. And if we want to convert that to hours, so that we have a better understanding of how long this actually is, there's 1 hour, there's 3,600 seconds in 1 hour, which is equal to 1.18 hours. So the alligator needs to sit in the sun for 1.18 hours to increase its body temperature by 5 degrees. And that's problem 12.36.